Assalamualaikum and a very good morning. Okay, so we have discussed on the parameters related to the antenna. So now we are going to look at the first step in designing an antenna. So we are going to start with wire types of antenna. So for example, dipole antenna and Yagyuda antenna. Okay, in order to design an antenna, so we need to consider the electromagnetic wave radiation. So in which to have a radiation, so there's a charge movement, the acceleration and deceleration of charge, in which does electric field and magnetic field produce. Okay, that's current flow. So we need to deal with the Maxwell equation as well, especially the electric field across surface area and also the line current or electric field across a thin wire, for example. So some basic properties of electromagnetic wave. So in which we have the electric field, the E field, and also the H field. So we have the E and also the H field, in which the field will be transported across or in free space. And so basic properties of electromagnetic wave, it propagates out in all direction, and then in high velocity, okay, there's acceleration, and also fulfills the Maxwell equation. Okay, let's recall the radiation mechanism, how radiation is created. So we have discussed this in earlier topic, okay, in which when we have a current flow, okay, over a wire. So when there's no movement, when there's no movement in charge, so the current is not created, therefore there's no radiation. So when there's a movement but with constant velocity or uniform velocity, so still no radiation unless the wire is bent, discontinuous, truncated, or terminated. And if charge is oscillating, okay, there's oscillation in time domain or its time varying field, although the wire is straight, so there's still a radiation. Okay, so consider a wire. Okay, for example, this is the wire. Okay, so A is the surface in which the field or the charge pass through, and consider the volume, and E is the electric field. In this case, it's in Z direction. And then we have the Vz. So Vz, small letter Vz, representing the velocity in Z direction. And we have the J is the current density. Okay, so when you have wire or a conductor, okay, there's charge on the surface. Okay, when there's current supply, okay, so there's acceleration of the charge on the surface. So the charge is moving across the area of A. Okay, so we can't estimate the total current density considering the charge Q, either it is a volume charge or surface charge, QS. Okay, A is the surface area, and V, capital V, is the volume. Okay, so in terms of mathematically, we can represent the current density equal to Jz, in which the current density in Z direction. So Jz, the current density in Z direction, equal to QV, the volume charge density, multiplied by Vz, small letter v, z, so the velocity. Okay, in case of ideal conductor, there's no loss, or it is lossless. So we can estimate the current density Js equal to the charge, surface charge Qs multiplied by the velocity. Okay, and for a very thin wire in which the radius is almost 0, very thin wire, so we can, so this is the length L, so we can estimate the current, total current equal to I equal to QL is the line charge multiplied with the velocity. Okay, so for radiation to occur, so we need to consider the time varying in which the there's variation in time domain or in time motion. So we can represent those equations into this, in which the current density is equal to L di over dt. Okay, time varying, and it is it can be represented as LQ Ez, in which A is the dv over dt, the acceleration. Okay, so L is the length of the wire, and QL is the line charge, and Az is the acceleration of the charge. Okay, next is the radiation mechanism for two wires. So when we have two wires, and we have AC source. Why we need AC source? Because we need oscillation. So when there's oscillation and time varying field, so that's it will create the electromagnetic wave, and so that's radiation. So this is the source, AC source, for example. So in between that's transmission line, so it end up with the antenna. Okay, so this is the transmission line. Okay, we assume the transmission line is in wire shape, in two wire shape. Okay, when we have two wires, so again there's positive and negative charge across the line. So when we have positive and negative, so we know that the field will flow from positive to negative. Okay, so if that's the source, so the field will flow from positive to continuously from positive to negative, something like that. So you create the electric field. Okay, same goes to the other side, and so on. Okay, we can see that the field basically penetrated within the structure. Okay, within the structure from positive to negative across the two conducting bodies. All right, so when it reached to the end, okay, when there's a flare angle, okay, where there's opening, so the field will continuously circulating within the structure until it is released into free space. Okay, so the movement of or the wave propagation or the electric field propagation, so in circular motion, so it can be viewed something like this. So we can see that how the wave basically traveling inside the structure until it is released into the free space area. Okay, so the time varying electric and magnetic fields between the conductors, so between the conductors within here creates electromagnetic fields, okay, and then it is released into the free space. Okay, and the signal or the wave will be transmitted via free space or any transmission medium to the end recipient at the end. Okay, so we have seen the comparison between the straight wire and also the two wires. So in this case, we are going to look at the development of a dipole antenna, which consists of two wires, as the second is almost similar as the second one with tapered or flat angles. But for dipole antenna, the one arm is bended to upper side and the other one to the bottom side, or one to the right and one to the left. Okay, so what happened when you have, if you still remember, when there's a wire, a straight wire, so there will be no radiation if there's no velocity or acceleration. So when you have two wires, but it is not truncated or it is not bended at the end, so what happens when you supply the source? Okay, when you supply the source here, so what happened is there's a field or the current flow in that direction. Okay, so and it is called incident or incident wave, and during the transmission there's also reflection. Okay, so on the other side, so when there's incident wave and reflection combined, it will form a standing wave. Okay, we have discussed this earlier. The standing wave generation due to the incident and also the reflection. And when you have two wires, okay, so one flow to that side and the other one flow to the other side, so the net current flow is 0, in which the field and the current cancel each other. Okay, so this lambda over 2 is the length of the standing wave propagation or oscillation inside the structure. Okay, so in these two wires, straight wires, there's no radiation due to the cancellation of the field or the current due to the top and the second conductor. And the two wires, the straight wire design is improved by having the flat angle, okay, at the bottom and at the top and the bottom, or it is tapered. So in this case, it's the same thing. Still, you have two wires on top and bottom. So there's still standing wave created with the length of lambda over 2 inside the conductor, but reaching to the end. So when there's a flat or tapered angle, so we can see that the distance between the two arms separated, so the total coupling between the two arms reduced, therefore the still signal successfully radiated. Okay, so the cancellation reduced, so there's still wave propagated into the free space. Okay, and the design is further improved by having the arm bended at one side and the other side, so in which the distance between one arm to the other arm is completely bigger. Okay, so therefore the maximum radiation can be produced. So in the next slide, I'll show you how the fields basically generated from this type of structure or dipole antenna. Okay, so let's look at the dipole radiation mechanism. So let's consider that we have the input source as sinusoid. Okay, so this is the duration is T/2, so this is T, one cycle, and here is T/4. So when you have a dipole structure, so at this point, okay, when the length is T/4, okay, at T/4 what happens? So let's consider we have a three positive and negative charge. So this is just for example. So we have positive charge here and negative charge here. So the charge will move from positive to negative. Okay, so the length is basically λ/4. Okay, so what happened when the length at T equal to T/2? So the stream structure so now at T/2, in terms of wavelength, it is λ/2. So what happened? So we know that at T/4, oops. Okay, at 0 until T/4, okay, this one. So we can see from on the other quarter, you can see that there's complete changes on the direction. This is upward and the other one going downward. Okay, so there's 180-degree reflection occur, or phase difference between that's changing in cycle. So the positive become negative and negative become positive. So in this case, from the first half up to this point, up to λ/4, so we have three charges just now, so maximum. So positive and negative. So on the next half, it's changing direction. So now the wave becomes like this. Till we have, let's have different color for this, up to maximum of λ/2. And assuming that we still have three charges, but now it changed direction. Okay, instead of top to the bottom, now it becomes bottom to top. Okay, this is when at T/2, or the length is λ/2. So when it reached to this point, Okay, so we can see that the magnitude is 0. So at that point, what happened is the field started to detach from the antenna. Okay, so at this point, the field started to detach from the antenna. So what happened? So we have the first three in the beginning in that direction, and we have the second one at the other quarter. 1, 2, and 3. Okay, so this one moving into that direction. So now when it start, the wave detached from the structure, from the antenna structure. So, and there's more than 3 charges actually. So you can see that when it is actually presenting a closed loop. Okay, we can see that the charge basically moving something like that. Okay, so the wave will be leaving the antenna structure into free space. So in this case, at lambda over 2, when the length of the antenna is lambda over 2, it reaches its maximum or optimum radiation. Okay, this slide basically shows the difference between the current distribution when you have different length of antenna. Okay, as shown in previous slide, when you'll have maximum radiation when the length of the dipole antenna is equal to lambda over 2. So what happened when you have different length of the dipole? So for example, the first one, when we have a small dipole in which the L is less than lambda, is much lesser than a lambda. So we'll see that the current may appear as triangular shape. Okay, when the L, in this case L equal to lambda over 2. Okay, so we have the maximum radiation at the center. Okay, so maximum at this point. And when we have the L is larger than lambda over 2 but lesser than lambda in the third case, so when the L is larger than lambda over 2 but lesser than lambda, so we'll see some some distortion in the middle, or the signal being cancelled at some point. So it reduces its maximum radiation at the center. And the last one, when we have the L larger than lambda and less than 3 lambda over 2, so we see additional signal or wave introduced, okay, in between the upper and the bottom arm. So this is to conclude that in order to design an antenna, we need to know the direction, okay, which are the maximum direction of radiation we need, so that we can determine suitable types of antenna with suitable size. Okay, this slide represents the current distribution on the same size of lambda over 2 but at different times. Okay, so different times means when you have this cycle, so what happened at different time interval. So for example, at t equal to 0 here, okay, this is your t, and then what happened when t Okay, in the middle, this is T over 4, here is T over 2, and here you have T over 8. Okay, so what happened at T over 8? At T over 8, when the cycle is somewhere here, so you can see there's still radiation, but it is not maximum yet. Okay, it just 0.7 or 7 of the maximum current. Okay, at T over 4, what happened? And then at T over 2, this point, and then at 3T over 8. Okay, so we can estimate the total current exhibited by at different time interval based on the same structure, or lambda over 2 dipole antenna. Okay, so we have seen how the radiation is generated by using single wire and 2 wires up to dipole antenna radiation mechanism. So next we are going to analyze the dipole antenna radiation mathematically. Thank you.